Hello, welcome to this video on the Lorenz group. So in this video we'll be using the ideas of spin and matrices developed by Pauli to understand how spin arises from relativity, and in the process we'll be uniting ideas of rotation in three-dimensional space with the concept of kind of Lorentz boosts and Lorentz transformations. Now, I've released a earlier version of this video yesterday. There were a few kind of technical details which I'm releasing this video again today, but with those kind of technical details kind of like ironed out. So if you've seen this video, appear before, that's why it's also appearing again now. But this video is going to be about combining Lorentz transformations and rotation in order to understand spin, relativistic quantum mechanics, and that will eventually help us understand tachyons and the quantum mechanics of tachyons, because tachyons are so relativistic that we can't really understand the quantum mechanical properties without relativity. So we need to understand relativistic quantum mechanics, and for that we need to understand spin and spinners, and it's nice to tie everything together into a Lorenz group. So that's what we're going to be kind of focusing on during this video. Also, if it's the first time watching this video, and if you're watching this video in the month where I've recorded it, wanted to wish you, very, very advanced. Hope you have a brilliant start to December. Although, given the nature of YouTube, you may be watching this video sometime in May, but I hope you have a very good Christmas season coming up that year, in that case. And on this channel, hopefully do a few kind of Christmas stuff before we reach kind of Christmas Day itself. So for this video we're going to be breaking down really this video into four key parts, as we're trying to relate Lorentz transformations with rotations to get a clear picture for what spin really is, and how Pauli matrices plays into that connection. So the first part we're going to do is we're going to look at introducing the Pauli matrices. So we're going to look at their properties. We're going to look at kind of relationships between different Pauli matrices, and we're going to look at their connection with how objects which have spin, mathematical objects which really describe the spin of something called spinners, transform and evolve in relationship to their spin. Then we're going to move on to talking about distilling 3D Euclidean rotation into the part of that rotation, or the part of the rotation matrix which is really deeply significant, and that part is called the generator. And it will become clear when we come on to it why we call it the generator of 3D rotation. And given we want to connect Lorentz transformations to 3D rotation, we'll then find the generators of the Lorentz transformation before kind of like bringing it all together, although there will be hints along the way over how it all connects, but in our last part we'll bring it all together to get a good understanding for what spin is. So this is how the video is broken down. For this video there's going to be bits of matrices in it. We're obviously going to make use of relativity, but all of the stuff we need for this video we've covered previously on the playlist, and particularly given I'm coming back to this playlist after a while, I won't be going through anything at breakneck speed. So join me along for the ride, and I look forward to seeing where we'll end up. There will be a bit of maths, and a chance for you to kind of derive something in this video. So if you wanted, I would recommend having pen and paper at hand. Otherwise, just kind of follow along as we journey together to really understand what spin fundamentally is. So the core matrices we really need to talk about if we look at spin and the connection between the Lorenz transforms and rotation as the Pauli matrices, which if you've looked at spin before, such as if you've looked at Dirac's equations and solutions to Dirac's equations, you probably would have seen them. So here are 4 Pauli matrices. Now, the Pauli matrices are strictly defined by their algebra, so how they multiply, and commutators between the Pauli matrices. So this is only one way of representing them. So, if you've seen them shown before with different numbers as their components, that might be practically equivalent. Because the Pauli matrices themselves, aren't, values for observable, so it doesn't matter if you write them, slightly differently, you're not contradicting anything. The important thing with the Pauli matrices is their algebra. So the Pauli matrices have, in this example, subscripts. Most of the time they have subscripts, and the importance of the subscripts is to imply really whether we're talking about time or space. So 0 is usually referred to as kind of like the time component for a 4 vector. Because the Pauli matrices don't form a 4 vector, at least not that I'm aware of, we tend not to talk about 0 as the time component. But 0 is usually referred to as a time component in relation to vectors, and then all positive whole numbers after that are referring to as spatial dimensions. And because in space-time, at least in conventional space-time, and all of this is working with kind of conventional physics for this video anyway, there are 3 dimensions of space. We consequently got to have 3 Pauli matrices in addition to our first one. Our first one is sigma 0. And in this video I'll be switching from the index with numbers to the index with letters, so like T, X, Y, and Z, fairly fluently. And the Pauli matrices are Hermitian matrices, because if we have a Pauli matrix and we take its Hermitian conjugate, we get back the original Pauli matrix. And we get the Hermitian conjugate by applying the dagger operator on the matrix, and the dagger operator transposes it, so it flips the off-diagonal components, and then turns all the components into their complex conjugate. So, for example, if we were going to do if we're going to find the Hermitian conjugate sigma 2, so find what we get when we act the dagger operator on sigma 2, we first have to transpose it, which would flip the I with the minus I, but then once we'd taken the complex conjugate of the transposed matrix, we would be left back with sigma 2, so we would get back to where we started. So all the Pauli matrices, including sigma 0, are Hermitian. And that tells us that these matrices could potentially be the kind of like operators referring to some physical observable. And and that physical observable is generally, in this case, with the Pauli matrices, spin. So it's telling us that these Pauli matrices refer to some physical observable, or at least have the potential to. And if we want to understand more about this physical observable, we can look at the commutation relationship between the spatial parts, the spatial Pauli matrices, if you like, so sigma 1, 2, and 3. And between these three matrices, we have a kind of a cyclical relation between the commutators. So if we take the commutator between sigma 1 and sigma 2, we'll be left with some, fraction, like, of sigma 3. Now sigma 0 is an identity matrix, so it's not doing anything. Given that 0 is generally reserved for time, that's indicating that spin should, it should be a property where, spin has no effect on the time components of a full vector. However, the kind of like Pauli matrices that refer to space have a cyclical relation, which is a lot like the cyclical relation between operators of angular momentum in quantum mechanics. So it's also implying that spin as a physical observable should be analogous in some ways to angular momentum, which is a pretty good start, I think, to understanding these Pauli matrices. But now we're going to have a little look at spinors and how spinors relate to these Pauli matrices. So to understand spinors, we have to understand how spinors transform. Now, spinors, as a first introduction, are eigenvectors, or in the context of quantum mechanics, eigenstates of our Pauli Hermitian matrices. And these eigenstates are eigenstates in terms of the quantum spin of the object. So our Hermitian matrices, our Pauli matrices, have associated with them these eigenvectors, or eigenstates. But the natural question is how these eigenstates evolve, and they evolve in terms of a unitary matrix. And just as you could get the unitary matrix for how something evolves in time by considering the Hamiltonian, which is officially a kind of Hermitian operator describing the energy of a system. Similarly, you can get how these eigenvectors of spin, so our spinors, will change, but using our Pauli matrices. But we have to, the changes are given directly by a Pauli matrix. It's given by a matrix, a type of matrix we can build out of our Pauli matrix. And this thing describing the evolution of spinors is essentially a unitary matrix, where the Hermitian matrix that goes into constructing it will be one of our Pauli matrices. So what is a unitary matrix? Well, to start with, a unitary matrix has this kind of form, where the components across the leading diagonal match each other, and I say the components match each other, I mean the magnitude or the modulus of the components match each other, and the modulus of the components off the diagonal also match each other. And I've written both U and its Hermitian conjugate here. Now if we multiply them, we end up with this expression. Now clearly, whatever A and B are, the off-diagonal components of U dagger U are going to be 0. And that leaves us with this expression for a unitary matrix. Now, we can go a bit further. We can, insist that the magnitude of a squared plus the magnitude of b squared is 1. And when we do that, we essentially have a unitary matrix. Now, importantly, A and B, can be complex, but the important thing is that a unitary matrix U is one where U dagger times U gives us back the identity matrix. And a spinor will transform via a unitary evolution which has one of our Pauli matrices as one of its emission matrices. So a spinor is an object which describes the state of an object with components that refer to the object's spin. And so our expression for the unitary matrix is e to the I times a Hermitian matrix. And it turns out, that, providing the H is a Hermitian matrix, we will always get a unitary matrix by taking, e to the I H. But our Pauli matrices are the Hermitian matrices corresponding to spin, so, a spinor will evolve according to a unitary matrix given by e to the power of I times a Pauli matrix. So the Pauli matrix describes how spinors evolve, and spinors are, if you like, the wave function version of particles, describing particles in terms of their spin. However, a spinor is very unlike a wave function in many respects, because, whereas, a wave function arises without worrying about relativity, spin emerges from relativity. Unifying relativity with quantum mechanics. So spinors don't really have a non-relativistic counterpart, but they do describe the state of an object in terms of its spin, and are in that ways, a lot like a wave function in many respects. So we talked a little bit about the Pauli matrices, but now we're going to go into the world of 3D Euclidean rotation, so just rotation in kind of everyday space. And we're going to see how the Pauli matrices relate to that kind of rotation through looking at infinitesimal rotations. Because it turns out when you look at infinitesimal rotations, you capture the essence of a rotation, and that essence actually relates to the Pauli matrices. And any macroscopic rotation is just built up by a very large, technically an infinite number of infinitesimal rotations. So this infinitesimal rotation contains all the core information we need to understand rotation in kind of Euclidean geometry. So here I wrote the rotation matrix for something rotating about the z-axis, such that its angle on the xy plane changes. Hence, I wrote theta xy to emphasise it's the angle on the xy plane that kind of is changing as something rotates. Now this is a 2x2 matrix if we're just considering how the matrix affects the x and y components of a full vector. However, if we want to consider the effect of the rotation on the whole full vector itself, so on a vector that lives in space-time, then we need to include all 4 dimensions of space-time, including time and the z-axis. So we can rewrite our rotation matrix in the context of full space-time as this 4x4 matrix. Now you'll notice that I have put the original 2x2 matrix in the middle of this 4x4 matrix we have at the bottom, because the second row and the second column and the third row and third column, where we have elements within that kind of realm, we have kind of our XY components of our 4x4 matrix. For example, the cos theta xy, to the left hand side, diagonal left hand side, of the one at the bottom is referring to the YY components. So it's referring to partly how the y coordinate of our 4 vector will change. And at the top left-hand corner of our rotation matrix we have a 1, because when we rotate something in Euclidean space, that isn't a transformation that is affecting time in any way. Rotation in Euclidean space only affects dimensions of space, and it doesn't affect the coordinates of the 4 vector concerning the component which relates to the axis of rotation. The z component of our 4 vector won't change, so there's number 1 at the bottom right hand corner of our 4x4 matrix. Now, if we want to get infinitesimal rotations, we just want to replace theta with d theta, where d theta is an infinitesimal angular displacement. But our kind of rotation matrix doesn't contain theta, it contains functions of theta, so we need to work out what happens to these functions as theta gets really small. And to do that we can use the small angle approximations which come from the Taylor series. So we have sine theta being approximately equal to theta, and cos theta being approximately equal to 1 minus theta squared over 2 for small angles. Now, if the angle is really, really small, and d theta being infinitesimal is unimaginably tiny, then sine theta is practically, sine d theta would practically just be d theta, and cos d theta would practically just be 1, because the d theta, let alone d theta squared, is going to be tiny and completely insignificant compared to the 1, and therefore our kind of infinitesimal rotation matrix looks like this. Now we're getting close to bringing powder matrices, but to do that we have to extract the necessary vital information contained within this 4x4 matrix we have in the blue box. Because most of the information within this matrix is actually quite redundant. I mean, the ones, along, at least the top number 1 on the top left hand corner and the bottom number 1 on the bottom right hand corner are not saying anything useful about what a rotation does. They're just saying what a rotation doesn't do. They're saying it doesn't change the time component, or in this case the z component of our 4 vector. The actual important information is all contained within the middle of this of this matrix. And so we're now going to get something we call a generator by getting the important information out of this 4x4 matrix for infinitesimal rotation about the z-axis. So now we're going to want to find our generators, and we're going to find the generators of rotation, so that is radii Euclidean rotation. And remember, the rotation of an object can be described by doing an infinite number of infinitesimal rotations. So just to describe rotation, all we needed was the infinitesimal rotation matrix we had on our last slide. But this infinitesimal rotation matrix contains a lot of fairly redundant terms. Particularly the ones in our leading diagonal are not telling us really anything at all that is relevant to the rotation, apart from what the rotation is not doing. For example, the rotation, the infinitesimal rotation is not changing the time component, it's not changing the z component. And when we're considering an infinitesimal rotation, there are other things that also aren't being changed. The significant really part of this infinitesimal rotation matrix can be extracted by just pulling the number 1 out of it. Because we really want to write we ideally want to write rotation, which you can think of an object rotating as some kind of evolution of the object. It's related to the angular momentum of the object. Since this is essentially really we want to think of rotation as a evolution, as a unitary matrix. We worked out before we can write that as e to the I times some Hermitian matrix. So we can get e to the I something by essentially taking the limit of 1 plus I times some matrix multiplied by an infinitesimal angle, or to the power of n in the limit where n goes to infinity. So we can build up a macroscopic rotation if we try to get infinitesimal rotation in the form of 1 plus I to the something times d theta. So that's why there's this I that's coming up before our 4x4 matrix. And then we're left with this 4x4 matrix. Now, we really want to give this 4x4 matrix a special name. And the name we really give it is, well, we call it the generator of rotations. It's essentially the interesting and important parts of our infinitesimal rotation matrix, which then allows us to describe rotations very generally. And there's something really special about this generator of rotations. This generator of rotations contains a Pauli matrix. Essentially this this generator of rotations, it's describing something changing its angle on the xy plane, but the important parts of this matrix are essentially its xy components, so components sitting on the second row and third column, or second row and second column, or third row and third column, or third row and second column. Essentially it's the x and y terms which are significant, and those x and y terms are the, are a Pauli matrix. And this is telling us something immediately very interesting. It's telling us, well, good, we've got a generator which is going to be Hermitian because it's essentially built built out of really the significant part is built out of Pauli matrices which are Hermitian. And that's good because it tells us that we can describe rotations in terms of these generators, where these generators are Hermitian matrices. But it's also telling us that fundamentally rotation can be described by the same set of matrices which describe quantum spin, indicating that an object with quantum spin should have an observable called spin, where this spin has the same units as angular momentum. So now we've got essentially an expression for the generators of rotation. Let's move on to considering what the generators for Lorenz transformations may be, and then we'll see that actually using those generators we can get generators of rotation, thus linking Lorenz transformations, so if you like, rotations in space-time with 3D Euclidean rotations. So if you want to get kind of a link between rotations and Lorenz transformations, we need to look at infinitesimal Lorenz transformations and get the generators from that. And the procedure is exactly the same as what we've done for Euclidean rotations. So we start with the macroscopic transformation, which in our case will be a Lorenz transformation in terms of hyperbolic angle phi. And phi is a function of relative velocity, so this Lorenz transformation describes how the components of a four-vector change when you go from one reference frame to another, where the other is moving with some velocity relative to the first reference frame. Now, when I've uploaded the video yesterday, instead of writing a Lorenz boost, to avoid lots of minus signs, I wrote a inverse Lorenz boost, which is a valid type of Lorenz transformation, because it's preserving the length of a four vector but changing the time and one of the space components of the four vector. But we haven't talked much about inverse Lorenz boosts, so when I've gone over this video again, I've used the Lorenz boost we would have seen in earlier videos on this playlist. So we have this kind of 4x4 matrix. It's worth saying in earlier videos on the playlist, I might sometimes reduce this to a 2x2 matrix, because the important parts of this matrix can be expressed, as like the 2x2 block we see on the top left-hand corner of our 4x4 matrix. That's the important parts, because that's the part that describes how the time and x-axis components of our four vector are changing as we go from one reference frame to another. So this is a Lorenz boost along the x-axis. Now, if we want to get an infinitesimal, Lorenz transformation, if we want to get an infinitesimal Lorenz boost, then we need to look at explicitly what cosine and sine are in terms of our hyperbolic angles. So in the black box at the bottom, I've wrote the definitions for sine and cosine. As a side note, an interesting thing is kind of like cosine of phi has kind of even parity, whereas sine of phi has odd parity, so that, slightly different functions. Both have symmetry, but a different kind of symmetry. Maybe that's, mildly off topic. The main thing is the definitions. And if we want to get an infinitesimal Lorenz transformation, we replace phi with d phi, and we're also using our definitions of sine cosine to see that sine d phi should be just d phi, whereas cos of d phi should be 1. Using the idea that d phi, is much, much smaller than the 1, and also d phi squared is going to be negligible in both the expressions for sine d phi and cosine d phi, because d phi is tiny, so d phi squared is going to be completely ignorable. And that leaves us with this matrix for the infinitesimal Lorenz transform, which I've broken down much like I did for the infinitesimal rotation matrix into the identity matrix, and then another 4x4 matrix which contains all the important information, and the other 4x4 matrix is your generator. So Kx is the generator for Lorenz space along the x-axis. And in this video, I'll be using K to refer to generators of Lorenz boosts. And we can see something a little special, because if we look at the x and kind of t components of our Lorenz boost generator, we see that we have present there, we have a Pauli matrix, really, or some scalar multiple of a Pauli matrix, which is again indicating that Pauli matrices are actually hidden in the generators of Lorenz transformations in much the same way that they're hidden within the generators of Euclidean rotation, implying that, fundamentally at an algebraic level, how we get rotation and how we get Lorenz transformations are kind of equivalent in many ways. So now we've got we've got a generator of Lorenz boosts. Let's find another generator. This will both help us have a bit of practice with working out generators, because I know, finding generators is probably a fairly new thing. But additionally, if we have a couple of Lorenz boost generators, we can see how we can start combining them together. And that will really help us tie Lorenz boost to Euclidean rotation. So let's find the generator for Lorenz boosts along the y-axis. So for this, we start with the kind of Lorenz transform that looks very similar to the Lorenz transform we had before, where the boost was along the x-axis. However, since now the boost is along the y-axis, it's the y and t components which contain the hyperbolic functions. But it's essentially practically the same. And then we can we can just take out a kind of identity matrix from our Lorenz transform, leaving us with a rather cool looking 4x4 matrix. And then we replace our macroscopic angle phi with our infinitesimal hyperbolic angle d phi to find our infinitesimal Lorenz boost along the y-axis. And then from the kind of like 4x4 matrix, we can get to the generator, which I called ky, and ky looks like this 4x4 matrix. So we have now derived the generator for boosts along the y-axis, and on the last slide we derived generators for boosts along the x-axis. Now let's look at kind of combining them together and seeing what we end up with. So we have our boosts and we want to combine them together, but the question is, what would be a physically meaningful way to combine them together? Do we just multiply them, or do we do something a little more elaborate? And it turns out, due to a particular special transformation that unitary matrices are involved in, called a similarity transform, which at some point I'll make a video on. The useful way to combine our Lorenz boosts is through using a commutator. So we've got the commutator of x and y given here. And you know, this expression is true by definition. This is kind of defining the commutator. And now if we put in the matrices for the boosts along the x and y axis, and we put in the explicit 4x4 matrices as their representation, we end up with this rather complicated looking expression for the commutator between kx and ky. Now, it looks really complicated because it's just really big. The matrices are really big, they're 4x4. However, the matrix multiplication works the same way as with possibly more familiar 2x2 matrices. And if you go through the matrix multiplication, you end up seeing that kx and ky, when commuted together, give us, as you would expect from matrix algebra, a 4x4 matrix. But interestingly, this 4x4 matrix is some scalar multiple of a rotation generator, particularly rotation along the z-axis. And this is telling us something really cool. It's telling us, and you can see this formally through the use of kind of like unitary matrices, and considering things like similarity transforms, but we can kind of see a very strong hint of it on this slide, that a Lorenz boost along one axis followed by a Lorenz boost along another axis is equivalent to a rotation about the third spatial axis. And so we can kind of generate, we get something equivalent to Euclidean rotation by successive Lorenz boosts along different axes, and we call this kind of rotation a Wigner rotation, although I'm probably mispronouncing that, and I apologise to any audiences who may be more familiar with the correct pronunciation. But we also sometimes call it a Thomas rotation. I'll probably call it a Thomas rotation because I'm confident with how to pronounce that correctly. But I apologise to any fans of the other scientists out there. And because we have a clear connection now between generators of Lorenz boosts and generators of rotation, not only do we have a physical way of interpreting this in terms of Thomas rotations, there seems a mathematical connection, but the mathematical connection actually prevents the kind of generators of Lorenz boosts forming a group under the operation of the commutator, because when we apply the commutator between two different Lorenz boosts along different spatial axes, we get something that isn't a Lorenz boost. I mean, we get something that is a generator of a Lorenz boost. We get a generator of Euclidean rotation. However, we can get a group if we start considering the rotations around Euclidean space and the generators we can get a group if we consider rotations around Euclidean space and the Lorentz transformations themselves together, and therefore correspondingly link, or have a group which features the matrices which are generated through our generators of K and the J generators. And before we move on to talking about the group that contains the Lorentz transformations and Euclidean rotation matrices, we're going to kind of touch a little bit on, to build towards that, we're going to touch on something called representation theory, which will go deeper into really unifying our boosts, our generators of Lorentz boosts and also our generators of our rotation. So to get moving towards a Lorentz group and really unifying Euclidean rotations and Lorentz boosts, we need to cover a topic called representation theory. Now, if that word sounds alien and a bit strange and confusing, don't worry. It's not something that is often looked at until you get so far into maths and physics, where you start thinking of the things you're writing not as defining a mathematical object or idea, but as describing it. And to illustrate the difference between defining and describing, that's, imagine I had a flower in a pot. When the flower is nice and alive and healthy, I might ask a biologist to define it, and if they were going to define it, they might start talking about plant cells and the different organelles within plant cells compared to animal cells, and about how minerals and water is transported across a plant, and how that is different to how minerals and water are transported to cells in an animal. And all of those things would define possibly the plant. But maths is really, when we write down maths, we're really describing ideas. We're not defining things most of the time. I mean, we can in very general ways. But a lot of the time when we say this equals this, the equality works, but it's talking about an idea, and there are many different ways to write down the maths which will correspond to the same idea. For example, with if we're considering representations of the flower in the pot, somebody might draw a painting, another one might make a clay statue of the flower. They're all valid representations, but very different. I mean, the picture will be 2D, the sculpture of the plant will probably be 3-dimensional, so very different. They look very different, but they get the same thing across. And we can do the same thing with mathematical objects. I mean, if we've got a vector, if you've done a bit of vector algebra, you'll be familiar that you can add together basis vectors to build that overall vector. Your kind of basis vectors are like building blocks. However, you can pick different basis vectors. And And if you wanted to describe the same actual vector using different basis vectors, you would just need to change your components, correctly. So essentially there are many different ways to represent a vector in terms of its components. In fact, there's an infinite number of different ways, because there's an infinite number of basis vectors we can pick to describe the overall vector. But the exact same thing is true with the matrices. Because if we look at a Euclidean rotation matrix and the spin Pauli matrices, we see that they have very similar algebraic properties. I mean, they have very similar cyclic commutation relations. Both the rotation and the Pauli matrix have an identity matrix within them corresponding to, essentially essentially corresponding to no action at all, or the unitary matrix we would get from the identity matrix would just be 1. It would be another identity matrix. So, we have matrices in both Euclidean rotation and the Pauli matrices correspond to, nothing happening. As I say, they have very similar commutation relationships. They have the same underlying algebra, and so we can just think of Pauli matrices as another way of representing Euclidean rotation. Now, this might be a little bit surprising on a visual standpoint, because the rotation matrices, as we've discussed them, are SO4 matrices, whereas the Pauli matrices are SU2 matrices. So they have a different number of dimensions, and also rotation matrices, they're orthogonal, and they contain real components, whereas our Pauli spin matrices are unitary and contain, at least some of them, some imaginary numbers. So they seem very different. However, they have the same underlying algebra, and therefore, for all practical purposes, they're kind of the same. They're two ways of saying the same thing. So, SU2 and SO4 might look different, but fundamentally they're kind of really the same. And to emphasise this, if we look at kind of the generators for rotation and our Pauli matrices, we can see that they have very, very similar commutative relationships, and we can go from one to the other by replacing J with a half times sigma. And providing we keep the index the same when doing this replacement, all is well and good. So we can think of a half sigma as a representation of a Euclidean rotation generator J. And we also have seen in the last slide that Lorenz transformations are linked with the Euclidean rotation. So, if we can get rotation through rotation generators, and those rotation generators can be expressed in the Pauli matrices, surely we could get Lorenz boosts by writing the Lorenz boost generators also in terms of Pauli matrices. And to do that, we look at the commutation relationship between our Lorenz boost generators and our Euclidean rotation generator. And if we, compare the relationship to the kind of relationship we have for our Pauli matrices, we can see that we can get back to the commutation relationship for the Pauli matrices by just replacing ik with I sigma over 2, and also replacing your replacing your Euclidean rotation generator J with your relevant Pauli matrix. So the upshot is we can represent all our generators we have discussed in terms of our Pauli matrices, really unifying them together, and now we're going to go further with that. We're going to talk about the Lorenz group. Before though we do go on to talk about the Lorenz group, where we'll finish this video up, I put this slide in because I realise it is worth addressing a potential question that may emerge, and that is, since we can represent Euclidean rotations and Lorentz transformations, or at least their generators, and therefore in effect the kind of transformations themselves, in terms of Pauli matrices, why do they seem so different? Why is spin, so different from Euclidean rotation? Why can't we have quantum spin when we just consider, rotation and don't worry about Lorentz transformations or relativity? After all, we're expressing the generators for both in terms of Pauli matrices. Well, the important thing to remember is that if we're defining a matrix or representing it in a particular way, for example, if we're looking at how to express the Lorenz generators, we don't just worry about the basis matrices. We worry about the coefficients to those basis matrices. Just like when you're describing a vector, it doesn't just matter the basis vectors, it matters the components. And the components are different for your Lorenz boost generators being expressed in terms of Pauli matrices, and for your Euclidean generators being expressed in terms of Pauli matrices. The coefficients we put in front of the Pauli matrices are different. So in that way, these two things are distinct. Also, whilst they have the same underlying algebra, that is referring to both spin and the kind of observable link to rotation, so angular momentum, being analogous to each other. The fundamental mathematical behaviour of the matrices is about that similarity in the behaviour. However, spin, if we look at the Hermitian matrices for spin, we have 2x2 matrices with complex components, whereas if we look at the rotation matrices, we have a 3x3 in space or 4x4 in space-time matrix. Also, the rotation matrices can act on 4 vectors in space-time, whereas our Pauli spin matrices act on these weird things called spinors, which are have 2 components. So clearly there are significant differences between spin and Euclidean rotation, and I thought it was worth emphasising that, because I know in this video I'm talking about unifying things, but it's always important to bear in mind, clearly, there does at least appear to be, in many ways, many different things in the universe, no matter how much we might unify them in our mathematics. But anyway, now I've covered that, time to move on to our Lorenz group, where we'll wrap everything together and finish up this video. So now we've kind of like emphasised the similarity, the fundamental similarity, and also some fundamental differences between the Lorenz transformations and 3D rotations. That's introduce the idea of the Lorenz group, which really unifies our two types of transformations together. So we said before that the Pauli matrices, which are commonly thought of as the Hermitian matrices representing spin, well, these matrices have many lovely properties, each with their own physical significance. But one of the properties they have is they have a lovely cyclical commutation relation. At least the spatial ones do. For example, if we take the commutator between sigma 1 and sigma 2, we will end up with some multiple of sigma 3. And in that sense, we can kind of form, well, at least in the fact that it's closed, we form something like a group with our Pauli matrices. Whether the Pauli matrices do form a group will depend upon other things as well. I think they might, because but for that, no, I'm not. Yeah, I don't think they would. I would have to check that, because if we're looking at our space, our spatial Pauli matrices, we don't have an identity matrix, but if we include the time Pauli matrix, we will have an identity matrix, but we will no longer have a closed. Would be closed. Well, it would be, yeah. Well, actually, we might have a group, because it would still be closed, but it wouldn't necessarily be cyclical. But anyway, that's me going slightly off track. I apologise about that, but it's good to think. Yeah, for me to at least think through what I'm saying as I'm saying it. But anyway, at least with the spatial parts of the Pauli matrices, the spatial ones, we have a cyclic commutation relationship. We also have that, as it turns out, with the generators for Euclidean rotations. We don't quite have that, however, for generators of Lorenz transformations. And for generators of Lorenz transformations, this is not closed, because if we take the commutator, we get something that is a Lorenz transformation generator. It's a Euclidean rotation generator. But this commutation relationship between our Lorenz transformation commutators, lots of this video is filled with quite long words. But one useful thing with this commutation relationship is that it allows us to map from generators of Lorenz transformation to generators of Euclidean rotation. And we saw before that this allows us to express, based on the fact that the generators of Euclidean rotation can be written in terms of spin Pauli matrices, to express our Lorenz transformation in terms of spin Pauli matrices. So they have the same basis, matrices. So is there potentially a group we can make with both the Lorenz transformations in it and the rotations in it, the 3D Euclidean rotations, which will form a nice neat group? Because we can't get a group by just picking generators of Lorenz transformations, because we end up with something that isn't a Lorenz transformation. At least if our binary operation is the commutator between our matrices. So, yeah, we can do that, it turns out. And the group that contains all of our Euclidean rotations matrices, so that's if you like, 3 independent matrices, so one for rotating about the x-axis, one for rotating about the y-axis, and one rotating about the z-axis. And we've also got in that group our Lorenz transformations, and again, we have 3 independent one of those, so we have 6 independent matrices within this group. This group is called the Lorenz group. So we can get a closed group by putting into this group the Lorenz transformations and the rotations, and we'll also have 6 generators for this group, and the generators under the binary operation of commutation or commutator, those generators will have kind of like cyclical commutations. If we're considering generators for rotation and generators for Lorenz transformations collectively. And you might wonder, what is the special significance of this group? Well, the special significance of this group is, both rotations, so our rotation matrices, and the Lorenz transformations will preserve the length of a 4-vector in space-time. We built up an expression for the Lorenz transformation in terms of hyperbolic angles by considering the fact that Lorenz transformations have to preserve the length of a 4-vector, so that's kind of like given. But rotations also preserve the length of a 4-vector, because rotations in 3D space won't change the size of the spatial component of the 4-vector. Thanks to that they can't change the size of the 4-vector overall. Because if we're looking at a 4-vector and calculating its size, it doesn't actually matter the orientation of that vector in space, because it doesn't matter the size of the vector's individual x, y, and z components. What matters for the size of a 4-vector is the size of its time component, or its first component, and then the size of its spatial components collectively, where you get the size of the spatial components just using Pythagoras' theorem. So Lorenz group contains essentially the set of transformations which do not change the size of a 4-vector. They're, to use mathematical jargon, the isometries of space-time. And if we're looking for the unitary evolution described by the Lorenz group, so described by rotations or Lorenz transformations, but now thinking of them as part of the same group, we can represent it as the evolution as a unitary matrix, which is going to be e to the I of something, and that something has to be a Hermitian matrix. And what's a great Hermitian matrix, which both generators of rotation and generators of Lorenz transformations are referred to? It's the Pauli matrices. So we can pick those. And there are basis matrices. What do we want to use to describe the components, though, of the overall matrix for when we try and get rotation or Lorenz transformations? Well, for rotation we would want a Euclidean angle theta, and for for Lorenz transformations, we would want a hyperbolic angle phi. And the beautiful thing of this unitary evolution is that this now describes, the evolution or the transformation of an object as a consequence of a transformation or of any of the matrices or combination of the matrices within the Lorenz group. And that's quite powerful, really. Now, importantly, the distinction between Lorenz transformation and Euclidean rotation is still preserved because we cannot factorise out the sigma, the Pauli matrix, from this expression. And that's because we cannot add theta to phi because these are two different types of angles, so we can't add them together, just as, if you add a banana to a teacup, you will be left with a banana in a teacup. You can't add a banana in a teacup and end up with two bananas. So, that's really everything, really, for this video, because we now got to a place where we understand what the Lorenz group is, we understand how to get the matrices of the Lorenz group using generators, and that the generators can be built from the Pauli matrices. And that's really the crucial role of Pauli matrices. They unify rotations in space-time, be that rotations in 3D Euclidean space or full-blown rotations within space-time, where we're considering rotations, if you like, in a time and a space component of a 4-vector. Now, understanding this is really important if we're going to look at the quantum mechanical properties of tachyons, because tachyons are very relativistic. And also, by talking about relativity and how, the Pauli matrices provide a crucial role within that, this is also a good video for the relativity playlist, and it builds on a lot of the stuff we've been doing, and it really gives a much more unified picture to Lorenz transformations and rotations, which is kind of a rather poetic and nice thing to do, given how many times we've been talking about Lorenz transformations as rotations in space-time. It feels fitting that we've at long last unified them together. So I hope this video has been enjoyable. It's definitely been very heavily mathematical in its content, but hopefully fun and interesting to listen to. And I look forward to seeing you more for more wonderful physics coming up soon. And as always, wishing you all the best and a very good week ahead.